F1 brakes aren't your regular brakes, they're so sophisticated. They stop at 790 kilos of a Formula 1 vehicle that travels in 200 miles per hour in the matter of 4 seconds.
These brakes are so strong that when a Formula 1 car can decelerate in 5 to 6G, a space shuttle can only decelerate in 3G. During the deceleration, driver's head weighs over 50 kilos due to 5G load. That's also why drivers do a lot of neck trainings. If a driver tried to push the pedal in a standing Formula 1 car, he actually wouldn't be able to push it hard enough. So the driver uses his weight multiplied by the 5G force during deceleration towards the pedals to generate the pressure they need to push the pedal.
Purely up to us to maximize the braking potential. We always want to brake as late and hard as possible using the downforce.
In other words, during braking, their bodies slide towards the pedals, and thanks to this extra force, drivers can push the pedals. Your cars at home have a servo system that multiplies the pressure you apply on your brakes to provide that necessary force.
This car has ABS, an F1 car doesn't, so anti-lock braking system. Makes your life a bit easier in a road car.
Once the driver pushes the pedals, the pressure is applied to two master cylinders. One cylinder is filled with fluid connected to the front brake system, and the other cylinder is linked to the rear brake system. The applied pressure goes through the brake pipes into the pistons housed in the calipers. Calipers have 6 pistons. Those pistons push the brake pads and they clamp around the brake disc. The friction between the pads and the disc slows the car down. Brake pads are tightly fitted between pistons and the brake disc. The front brake system is this simple hydraulic system. Rear brake system is, on the other hand, a little more complicated due to energy recovery system, which we will talk about in a bit. Master cylinders are fed with master cylinder reservoir through the brake pipe. Master cylinder reservoirs hold 100 to 250 cc of fluids. You need these reservoirs because during the braking, the brake pads wear off due to thermal degradation. Therefore, the brake pads keep getting slimmer and slimmer due to wearing. So the pistons and calipers move further and further, creating a space. And that space needs to be filled with the fluid in the reservoirs. The little nozzle you see here is connected to the reservoir through a hole. Once the pedal is pushed, the shaft you see here moves, and the other end of the shaft, which is a piston and a seal, covers the hole. Now we have a closed system, and the incompressible fluid inside the cylinder chamber moves into the brake pipes. Master cylinders are connected and can float like this. This is to create the brake bias, which is also called brake migration. Brake bias precises how the force is shared between the front and the rear of the brakes. Ideally, you want each brake to do half of the energy dissipation, since it may cause understeering or oversteering. Roughly, the weight distribution is dissipated 45% front wheel and 55% rear wheel. Under heavy braking, most of the weight shifts towards the front wheel, so the brake bias sets up towards 55% frontwards. Too much front brake bias locks the front wheels too tightly, causing understeering. Too much rear bias would cause the back of the car locked too tightly, and car would spin or be unstable. Ideally, you want weight to be distributed equally, and when the brakes are pushed, both rear and front to lock equally. But if you have to make a choice, a bias favoring towards the front bias would be a better choice, since dealing with an unstable or spinning car is the worst case scenario you don't want to deal with. Drivers can adjust the bias from the cockpit, but this is only allowed when they are not on the brakes. The reason why this precision is left to the drivers is that each track and corners have different characteristics, and depending on driver's driving style, this balance needs to be tailored towards each incident. In commercial sports cars, calipers are vertical. For F1 cars, calipers are located low in the car to make sure the center of gravity is low, but rather than horizontally, they are located in 45-degree angles. The reason for this is that the bleed nipple needs to be high. This knob is called bleed nipple, and it should be located upwards since it is used to bleed the air bubbles that gets into the hydraulic systems. Failure to bleed this gas gives a squishy feeling on the pedals, especially because the compressible gas deforms in a system that essentially needs to be incompressible, which also decreases the braking force, hence the performance. To solve this problem, teams flush the gas by opening the nipple, then forcing more fluid into the system, so the gas travels up and out of the system as the nipple is located with 45 degrees angle. Emitter of the 6 pistons in the calipers are different because you want them to apply different forces. If the first contact piston is bigger, it would cause more wear as well as producing more heat since it's facing uninterrupted rotational speed. The way braking system works is that the kinetic energy of the rotating discs are converted into heat energy, and there is only certain heat capacity that these brakes can operate in. At temperature higher than 800 Celsius degree, thermal degradation kicks in. Under heavy braking, this heat rises up to 1000 degrees. As the pads clamp around the discs, kinetic energy is translated into heat energy via friction. If the discs are already warm, there is less ability to convert kinetic energy into heat energy. In other words, less ability to absorb energy. In other words, less braking capacity. That's why cooling system is very important. Brake discs are made out of carbon-carbon composite. It is a carbon lattice reinforced with carbon fiber. The reason for that choice of material is both high coefficient of friction and robustness at high temperature, since the temperature of brakes can get as high as 1000 degrees Celsius. Carbon-carbon also has very low thermal expansion as well as low thermal shock, so it won't deform or crack in sudden thermal changes. A cold brake can heat up to 100 degrees Celsius per every 1/10 of seconds. Carbon brake operates optimally between 400 and 800 degrees. Yet, heavy braking can heat brakes up to 1000 to 1200 Celsius degrees. The main factor a brake to wear off is thermal degradation. At high temperatures, carbon oxidizes, meaning the brake discs and the pads burn on the mating contact surfaces, creating a black dust while structurally disintegrating. That's the second reason why cooling is important, and the solution is air cooling, since we abandon cooling liquids in the brake system. These are called brake ducts. As the car moves, the air passes through the brake duct into the middle of the brake disc. Since the brake disc is spinning, the air passes through the cooling holes. Cooling holes are narrow channels on the disc that pass from center to circumference. The air molecules emit the heat and simply flow away. Over the years, the air cooling holes decreased in size and increased in number, providing more surface area to exchange heat. Larger brake ducts can create more aerodynamic drag, but it's not that significant on vehicle's pace. The actual concern and reason to adjust the size of these brake ducts is the nature of the circuit. If a track has a lot of corners, like the track in Monaco, brakes will be used more frequently, and you need a more intensive cooling system. You simply don't want to enter braking zones at 800 degrees. In that case, to increase the number of air molecules that interact with the disc, you should enlarge the brake duct, therefore the air intake. On the other hand, brakes don't work really well when they are cold. That's also why drivers don't really feel comfortable on their first corner of track, since brake discs aren't hot yet, so they don't know how much brake they can get. If they don't press the pedals hard enough, they can lose advantage since they won't attack corners as aggressively. If they press brakes too hard, they could lock out the brakes. You want brakes to be at least 400 degrees to hit the brakes. So if you aren't braking too much in the circuit, there are long periods of time between braking zones and air can cool the brakes too much. To prevent that, brake ducts need to be smaller. Some teams also tape the brake ducts to block some of the incoming air that could cool the discs more than desired. If you brake when discs are cold, it will take 10th of seconds to kick in properly, which isn't ideal. Rear brake system is a little more complicated. In the rear brake systems, hybrid power unit concept comes into play. Rear brakes are operated by brake-by-wire system, which is also referred as BBW. Calipers are controlled by a computer servo system called electronic control unit instead of a hydraulic pistons. To clarify, for rear brakes, physical action of the brake pedal isn't directly linked to the physical action of the calipers. Instead, a computer system tells the brakes to what to do. MGU-K unit slows the wheels down partially since some kinetic energy is used by this unit to store power, and the rest of kinetic energy is converted into heat by rear brakes. The amount of energy MGU-K can harvest depends on battery levels, pedal pressure, brake bias setting, and harvesting settings. Electronic Control Unit (ECU) controls rear brakes. MGU-K pedal pressure, brake bias setting, and harvesting settings information is constantly fed into ECU. And ECU calculates how the deceleration duty should be shared between the brakes and the MGU-K. Since rear brakes have some help from MGU-K, rear brake discs can be smaller than the front brake discs. If MGU-K fails, however, rear brakes have to make up for it.
This is all. Thank you for watching. If you like my content, hit that subscribe button. But you don't have to. This is a genuine smile. I think next time I'll talk about suspension systems, and which is next week. I'm back, guys. I'm back. I was away because yeah, we will talk about that in more casual videos. This is a technical insight video. Bye.